Okay, so we're doing 23. Why don't you start by reading that over to yourself and then drawing it? So it rolls without slipping, so it's under the influence of static friction. Okay, so they're giving us information like inertia. Okay, so now we're not using a set equation, but they put it in terms of mr squared, so we're going to use the same process. They give you the radius, they give you omega. And they say to you, calculate H. So of our two techniques, writing sigma and torque, or writing conservation of energy, which one do you think we're going to use? I went through the first technique with you in the beginning class, and then we just had another with the second technique, which you went through in your notes. Right, conservation of energy. Because conservation of energy has H in it. So you're writing out your conservation of energy equation, as I went through with you. Now, this one's a little bit harder, right? Because we have this 2,600 joules of work. Friction does work as it rolls up the hill to a stop. But you're going to start with just getting your two types of kinetic energy, get your total kinetic energy just as we did before. So get that kinetic energy. See if you can get your potential energy, and then we're going to write out our total equation, including the work done by friction. I didn't have that work done by friction in the other problems we did, but you can get your total kinetic energy. Now you're going to get the kinetic energy in terms of what they gave you. Okay, so you have your two types of kinetic energy, 1/2 mv squared plus 1/2 I omega squared. You plug in for I, 0.8 mr squared. You cancel out your r's, just like before. So before I had something rolling down a hill, this is rolling up. So this is my general equation. I have potential energy, the top is 0. My kinetic energy is the 1/2 mv squared plus 1/2 I omega squared. We have our work not conserved. We have our potential energy at the top, which is mgh, and our final kinetic energy is 0 because it stops. So we're just kind of switching the equation. Instead of having mgh on the left, we have it on the right. And then we have this work not conserved. But you're plugging in the same thing, the two types of kinetic energy. You have mgh here. So they gave you the weight, and you can get the mass from that, the 392. So I have this equation in general, 1/2 I omega squared plus 1/2 mv squared minus 2600 joules is equal to mgh. So they gave us the inertia is 0.8 mr squared omega squared. We know that our v squared, you could have put this in terms of v or in terms of omega. Because they gave us the omega, a 25 radians per second, I left it in terms of omega, but you didn't have to do that, right? You can put in your v squared and cancel out your r's, and then get your v using the equation v equals omega times r. You might have found that easier. So you could have gone v squared over r squared, cancel out your r's like we did before. Cancel out those r's, and then get v from this equation right here. Now, we can't cancel out our m like we normally do because of this. But we can get our m based on the weight. They gave you the r. Okay, but you really didn't, you didn't really need the r. If you put it in terms, well, you need it to get your v here, I guess. Right? But in order to get the equation in terms of v, you don't need the r. So they gave you the omega, they gave you the R. Your weight is going to be 392. Your mass is going to be 392 divided by 9.8, which is 40 kilograms. And if you canceled out, if you plugged in for your, canceled out your R's and got it in terms of V, well, you can just figure out your V from, because it's omega times R. So whether you keep it in terms of omega or put it in terms of V, it doesn't really matter. You should get the same thing in the end. So your V is just 15 meters per second. It's 25 times 0.6. So you could have put it in terms of V. $15 meters per second. Show me if you get it. So if you're doing it this way, we have 1/2 times 0.8 times 40 times 0.6 times 25 squared plus 1/2 40 times 0.6 times 25 squared. If you put it in terms of, this would just be 15 squared and 15 squared. If you got it in terms of V, right, instead of 0.6 times 25, you just have 15 squared. So you add this to this, you subtract the 2,600. You should get 3,600 here. $4,500 here. Okay, so you get 5,500 on the left side of the equation, divided by 40 times 9.8 gives you 14.0 meters. All right. Okay, we're going to go to 27 after this. So just read it silently to yourself. subtract out. I think you didn't subtract out the group by friction. So you told us 2,600. So you add those together, subtract out 2,600. Okay, so let's go 5,500 divided by 40 times 36. So you're leaving 27 to yourself. Now we're using one of the two techniques, conservation of energy or sigma and torque. Which one are we using? Right, conservation of energy again. Again, it's rolling up the hill without slipping, so that means it's only static friction, no kinetic friction. A thin-walled hollow sphere, so you're using that shape. They're asking you omega at the bottom of the hill. Now you can just get your V in the way we went through, and from V get omega. So you're setting it up just like before. We're putting potential energy on the right rather than on the left. Plugging in for your I, doing the same exact thing. Plug in for your I, get rid of omega. In this time, you can go through the step-by-step process. It's the exact same thing we did before. isolate your V just as I taught you. So we have the usual 1/2 mv squared plus 1/2 times 2/3 mr squared v squared over r squared. We cancel out our r's, we cancel out our m's. We isolate our v, just as we did before. So you get 1/2 v squared plus 2/6 v squared is equal to GH. Then when you isolate this, right, we add those together, we get 5/6 v squared is equal to GH. So we get v is equal to 6/5, the square root of that times GH. Remember how I told you it always comes out to a fraction times GH? You plug in, you get your v. Once you have your v, then you can solve for the rest of it. Dakota, did you get the v?
7.67.
Good. You should get 7.67 meters per second. So now you can get your omega. Your omega is simply the v over r. And then you can get your rotational kinetic energy. We can get our omega, which is v over r, so we get 67.9 radians per second for our omega. Did you get that? Now, then you have to get your rotational kinetic energy. So we know we want 1/2 I omega squared, but you can, again, plug in for that. Once you know your V, right, you can just plug in for that I. We just got the rotational right here. So it was 1/3 mv squared. If I go back to look at my rotational right here, I cancel out my r's. I cancel out the 2. I get 1/3 mv squared was my rotational. You could have used omega squared to r squared as well. Spencer, did you get the rotational?
8.36.
Good. So the equation is 1/2 I omega squared. But I plugged in here 2/3 mr squared, canceled this out, canceled out the 2's, got 1/3 mv squared. So it comes out to 8.35. So I think what I'm going to have you do, rather than go on to working power, we're just going to start one of the other ones that I skipped over, which are some harder ones. So I skipped 25. So it's a harder one. We're not going to have time to finish it, but I think that's the only one I skipped, right?
I think so.
All right, we're just going to start 25. Dakota, can you please read 25?
A thin-like string is wrapped around the outer rim of a uniform hollow cylinder of mass 4.75 kilograms, having inner and outer radii as shown in the figure. The cylinder is then released from rest. A. How far must the cylinder fall before its center is moving at 6.60 meters per second? B. If you just dropped the cylinder without any string, how fast would its center be moving when it had fallen the distance in part A? C. Why did you get 2 different answers when the cylinder falls the same distance in both cases?
So you can read that over to yourself. It starts out not that hard. If they're asking you about velocity, which technique are we using? The conservation of energy or the sigma torque? Right, conservation of energy. So just start out writing your conservation of energy equation. This inertia is harder, but you have your equation for this inertia. They gave you the R's. So you can work with the equation to simplify it, but in this case, it's easier just to plug in your R's. So you have your hollow cylinder 1/2 m r1 squared plus r2 squared. They gave you the m, they gave you the r. So why don't you start by getting the inertia of this object? Be sure to put that into meters. Once you get that inertia, it's not really that hard. You're writing your general conservation of energy equation. So we have the same thing. It falls, that's mgh. It's rotating and translating, that's 1/2 I omega squared. You're plugging in for your mass. And that you know the V, so that actually makes it easier as well. We can just plug in M, plug in V, plug in for our I. So plug in your I for your 1/2 I omega squared. Now, what do you plug in for omega? Well, we have V over R. Omega is your V com divided by what? Is it the sum of the two R's, or what is it we divide by for omega? Right. Okay, it's just your V com divided by 0.35. We're solving for that H. What did you get for your inertia? Anyone?
0.36.
Good. You can plug in for V, plug in for your inertia, plug in for omega. Okay, I'm going to let you finish this one at home. The other problems you have for homework are 18 through 28. Okay, so 18 through 28. So you have 6 problems, plus you're just finishing this one. Now, I think there's only like one in there that I'm going to give you a hint on 26. 26 is your sigma torque, is your sigma and your torque equation. Okay, so if you're looking at that one and you're confused, it's the sigma and torque equation, but hopefully you'll figure out the rest on your own. Okay?